30 milligrams per liter coming out of the undersized system, and 20 milligrams per liter coming out of the standard outlet. So that's a good thing to note. If you look at load reduction, so we're again taking the volumetric reduction that occurs in the bioretention cell and combine that with the concentration reduction that may be occurring in a particular pollutant. You compare the small cell to the large cell. Mind you, right, the large cell is going to cost you how much more than the small cell if it's twice as big? Twice as much, right? So you've invested twice as much in that full-size system that's designed for the 1-inch event, okay? So let's compare total nitrogen, 37 versus 45% mass load reduction. Which one would you buy? Okay. Total phosphorus, we had really, really low inlet concentrations coming in off the highway, so it was hard to, it's hard to clean water, basically, so we couldn't reduce the concentrations any further. So you can see we actually exported phosphorus a little bit from the small cell, 4% reduction from the large cell in mass of phosphorus. Sediment, 49 versus 56. Now if you're the developer, which one would you choose? I would choose 2 of the undersized systems if it's going to cost me the same thing, right? So this study really, really showed us undersized systems work very, very well because the majority of your storm events are still less than a ½ inch in size, right? Your 90% storm is going to be 1 inch. So your 70% storm might be a ½ inch. So you're still treating more than half of the 1-inch storm, even though the cell is only half size, if that makes sense. I'm not sure I'm saying that well, but question.
Do those effluent numbers include what was overflow?
Correct. Correct. So it's overflow plus drainage. Correct. Yep. Okay. So the undersized system worked better. Just want to point that out for those of y'all who may have retrofitting requirements. Undersizing these systems is not necessarily a bad thing. So take-home points, these things improve hydrology, both long-term as well as single storm hydrology, both load reduction in pollutants as well as peak flow mitigation and volume reduction. And they really, really get at all of our pollutants of concern very, very well. So this is really our best BMP that we have out there for stormwater treatment. And I think we're out of time, so I'm going to leave it at that. I had a construction case study that I was going to show y'all, but I'll leave it at that.
A rule of thumb for what the surface area of the bioretention needs to be?
Sure. So what we typically do in North Carolina is we calculate the volume of runoff coming off of the watershed. So for instance, 1 acre would be 1 acre inch of water, which is a great unit. If you say that unit in another country, they look at you like you're ridiculous. So they have no idea what an acre inch is. But 1 acre inch of water, and then what you do is you take that volume and divide by your bowl depth, which is typically 12 inches, and so you get 1/12 of an acre inch would be the size of the cell that would be needed. But in here you're actually getting more credit because you're getting credit for the porosity in the soil and the aggregate. So it would be somewhat smaller than that here in Atlanta.
If you're sizing your facility to handle channel protection volume as well, do you include that first inch of runoff volume in the channel protection volume as one, or do you sum the two?
No.
Your facility.
I'll let Corey answer that, but I would think it would be part of the channel protection volume.
Yeah. Okay.
Yeah.
Because I know in like extended
detention,
or wet detention, I think the state of Georgia allows you to use half of the water quality volume, but you still have to add that on top of the channel protection.
Yeah. Yeah.
But this channel protection includes, so you would size the facility for channel protection volume, correct?
Correct.
And that would include your water quality?
Yep. Another question?
Yeah. This year we just had an incredible amount of rain.
Yeah.
There's no such thing.
As have we.
Yeah, a 1 year or 2 years.
Yeah.
Getting 100 years.
Yeah.
Hyper.
Yep.
My question is, over this long period of time where we've had this extensive amount of water, if you have these conditions, is there over and over and over for extended periods of time, is there a degradation to this system because they really can't function the way they're designed to function?
The only degradation that I would see is if you had like some sort of failure in your berm. I mean, it can handle, the thing is like any BMP, it can't handle back-to-back storms as well because it's not fully drained out. So yes, if you have, for instance, Hurricane Floyd happen on day 1 and Hurricane Fran happen on day 2, Hurricane Fran isn't going to hardly get touched at all because the system's going to be full. But I think that would be the case with a dry detention system or a wet basin or whatever practice you're putting in the ground.
After it drains and
Then it's fine, yeah. unless you've got some sort of major berm failure that occurs because you've got so much water.
I'm
But
thinking of the media and everything.
no, the media would be fine. Yeah, media would be fine.
A lot of this stuff too, if you're thinking about back-to-back storm events, your first event is taking your water quality, is taking that initial flush of the garbage,
Right.
putting it into the media. Anything really beyond that.
Exactly.
I hate to say, it's not clean water, but
It's cleaner.
it's cleaner.
Cleaner, yeah.
Then it's coming off.
Yep.
One more question on sizing.
Sure.
Is there a limitation to the amount of contributing drainage area for per bioretention?
Let me answer that question with this really quickly. So this is a bioretention cell that I built at Lewisburg High School, which is one county northeast of Raleigh. The drainage area is this. It's 6 acres. So most manuals that you look at will say, oh, 1 to 2, 3, maybe 5 acres. You can build them a lot bigger. They can be built bigger. You're going to get, I would say you're more in the meld of low impact development if you have smaller distributed practices though. In this case though, if you look at that high school campus, where do you put distribute, I mean, it's really hard, right? And we had one outlet pipe at this location. And so it worked out to put a large system in. This was a 10,000 square foot bioretention cell, so quite large. Quarter of an acre almost. Question?
Specifically related to school,
Yeah.
do you have any experience or information about putting bioretention under athletic fields?
Under athletic fields. I've never seen bioretention done under athletic fields. I have seen like a gravel aggregate storage reservoir underneath, what do you call it, AstroTurf? So I've seen people try to design that as sort of a volume reduction device, if you will, where they route like rooftops into that aggregate storage layer underneath the field, and then they slowly let it infiltrate into the underlying soils. I have seen that designed and permitted. I don't know if I've ever seen bioretention underneath an athletic field, no. Yeah.
Ask a question.
Sure.
Compaction.
Oh, yeah. Yeah, compaction is a good question. So let me show you what happened on this site real quick. Here's the existing sewer pipe I was telling you about, 18-inch pipe for 6 acres. Those of y'all who are engineers, is that properly sized? No, it's way undersized, right? So we would get pressurized flow out this pipe all the time. So here's our existing conditions. It was just a field. There's the plan view of the bioretention cell that's going to go in. This is the existing inlet here. Quickly go through this. There's the cell design. We had this is the 18-inch pipe right here going right through the middle of our system, and we had to take that out during construction, and I will show you the disaster that occurred. So here's our contractor starting the excavation, more excavation. Here's our pipe, 2 feet down. This is the existing inlet and the pipe going down to a ditch along the side of the road. And you'll see we've dug out now down to 4 feet, and we would get pretty good infiltration into the underlying soils from the direct rainfall. Here's the excavation around the pipe. You can see the pipe right here. What do y'all note about that pipe? It's all scratched up, right? What did they do? They hit it with the excavator teeth, right? So what does that do to your pipe? Doesn't strengthen it, right? It weakens it. So on May 24th, we got 3.75 inches of rainfall in 2 hours. And we had lots of pressurized flow through that pipe. What do you think happened? That happened. There it is, right there. That happened. And so now what do you have? You have a 4-foot deep hole that's receiving 6 acres of runoff every time it rains. So what does that do to your construction budget? Change order, big time change order. You hear that word coming. So $7,300 change order. We had to pump it each time it rained. It was a huge pain. Here's the media going in. Used a long arm excavator to prevent compaction, and then they used skid steer loaders for the final grading to prevent compaction of the soil media. Here's what I wanted to show you. This is a graph. This is our typical bioretention media in North Carolina. Percent compaction, that's Proctor compaction on the bottom, 65 Proctor, 85 Proctor at the right-hand side. And then here's your infiltration rate from 0 to 10. This is the same soil, and you can see what compaction does to the infiltration rate. So you can come in, and if we're very careful and we're using what I just talked about, a long arm excavator with skid steer loaders, we might have a 65% compaction initially. That's going to compact down some. The first couple times it rains, that water is going to naturally want to compact that soil a little bit. We usually figure roughly 10% of the soil depth. So if you have a 3-foot depth, we think you're going to get roughly about 3 inches of media sort of compaction, or what's the word I'm looking for? Settling. Thank you. Settling. So you may have to come back in and top that off a little bit. But you can see what it does to your infiltration rate. Just a 10-fold decrease from 9 inches per hour down to 1, depending on what compaction rate you get to. So you have to be very careful. And there's one city, I guess I can say it, City of Durham, that will actually, if you get below the 1 inch per hour rate at installation, they will make the contractor tear it out and start over again. And you can imagine that happens exactly once to each contractor. And then they figure it out quickly, right? So we had an outlet structure as a broad-crested weir at this site. Here's the completed cell there. You can see it during a storm event. So it's a grass system with a couple of trees, basically, is what it looks like.
And why
So.
did you make it curvy?
It's the same engineer that designed the devil eyes earlier. So he likes to make things look pretty. So I'm not really sure why. It certainly adds the construction costs. Yeah. So I'll leave it at that. I'll take any more questions y'all might have, but if not, we can talk during the break and maybe take 10 or 15 minutes.
Yeah, let's take a 10-minute break and we'll start back on the 30th.
Okay.